In the last class, we have discussed how we can model a plate with a circular hole in ABAQUS and how to apply load, how to do the meshing, how to get the result, and how to plot our stress path. Today, we will try to extend it a little further. We'll see how much stress is generating here, what is the maximum stress is here, and what is the maximum stress as per our theoretical analysis. In the last class, we have discussed how we can model a plate with circular cutout, how to do the meshing, how to do the meshing, how to apply the loading, and how to get the stress pattern, how to plot our stress path. And now we'll try to see what is the maximum stress is generating as per theoretical analysis and how much maximum stress is generating as per our ABAQUS model. Here, just note one thing, this calculation need to be corrected. So this calculation, the average stress that is occurring here, that is your P, that is your total force. P is total force is 100 times that length here, total force is acting 100 times that length. Total force divided by the cross-sectional area. So total force divided by the cross-sectional area. So this is the thing you can do. The total force will be 100 into 50 Newton per mm. So this is the thing you can imagine. This is your cross-section, and here 100 Newton per mm load is acting, and total this is your 50. So total force was 100 into 50. 150 divided by your effective area. Effective area is 50 minus 10, okay, into your thickness is 5 mm. So if you do the calculation, it will come 25 mm. That is our average thickness, and maximum stress, that is our average stress, that is our average stress. Now the maximum stress that was occurring, maximum stress that can occur as per theoretical calculation, your average stress times your factor, stress concentration factor. Okay, average stress times your stress concentration factor. If you do that, it will come 62.75 MPa. So this is the maximum stress that will occur as per our theoretical calculation. Now we will try to see how much stress is generating in ABAQUS model, and then we will try to see how we can model for nonlinear analysis. Here, if you see the maximum stress, you sigma 11 or S11 here, that value is here coming 7.5 to 8. So if you note down that maximum stress is coming 7.5 to 8 E plus 1. So basically 75.28 MPa. This is the maximum stress is generating in our finite element model, and as per our theoretical one, it should come nearly 60. As per our theoretical calculation, it should come nearly 62.75. 62.75. So this is the theoretical stress, and our maximum stress as per numerical model is 75.28. Now, one more thing you have to keep in your mind, that we have not done the conversion study. You should do it. You should go for more finer mesh. Okay, you should go for more finer mesh, and you have to analyze it again, and you have to see whether the result is converging or not. Okay, so that converged result you should compare. So this is the way basically we should model a plate with circular cutout. Next, we will see how we can go for nonlinear analysis. Okay, and here you have to keep one thing in your mind, that once you go for nonlinear analysis, that time you have to keep in your mind what type of material is it, whether it is a ductile material or it is your brittle material. Depending on that, your nonlinear modeling will depend. One more thing you have to keep while going for nonlinear modeling, you have to concentrate on few parameters. One is your meshing. In meshing section, you have to have a good condition mesh. Poor element size may give a erroneous result. Poor element size may give erroneous result. Poor element size where one length of the element is very high in compared to the other length. Okay, if one length of the element, one side of the element is high in compared to other side, that element basically a poor type element. This type of element may not give good result. So whenever you are doing the meshing, that time you have to keep one thing in mind, that you are not modeling with poor element. One more thing you have to keep in mind, if there is stress concentration zone, in that case, there should be finer meshing. There should be finer meshing near the stress concentration zone, and you can use little bit coarser mesh away from the stress concentration zone. Now, while doing such meshing, you have to keep one thing in your mind. Keep one thing in your mind is that you should try to have a square type meshing. You should try to have a square type meshing, because square type is well conditioned mesh, well conditioned element. Square type element is a well conditioned element. But if possible, try to do it. Otherwise, you should try such that your L1 by L2 ratio is very close to 1. L1 by L2 ratio is close to 1. So this is the things you have to do in the meshing. Next is that your material property. Next thing you have to consider your material property. Now in the material property, again you have to realize what type of material is it, whether it is your ductile material or it is your brittle material. Depending on that, you have to give the material property. If it is a ductile material, in this case, you can give plasticity data. You can give plasticity data along with your elastic data. If we go for brittle material, in that case, along with your elastic data, you have to give damage parameters. Hassen damage criteria is there. There are various damage criteria there, depending on the material type, whether it is your granular material or that is your fibrous material. Depending on that material, you have to give your damage parameter. If you are doing your static analysis, in that case, your loading should be smooth enough. Either load can be in the ramp fashion, which is increasing monotonically, or load can be in a smooth step fashion, or load can be in a smooth step fashion. Okay, either a ramp or in a smooth step fashion. Now here, what we are doing, since our analysis is static, we are giving the incremental load very small. At each step, we are providing very small loading, and we are doing the analysis. So what happens if we do small loading? If we time T1, this is time T2, time X, this is load. Now, if you give a small increment, in that case, the load also, if you give small time increment, in that case, load also will increase small amount. And if load increase small amount, in that case, you will be able to capture stress strain behavior properly. For example, if this is your stress and strain behavior, okay, at time T1, this is your stress, or here strain, you can say. At time T2, and at time T2, this is your stress and this is your strain. So now, if your time increment is large, in other way, if your loading is large, in that case, you will get this point and you will get this point. So in between data, you will not able to capture, and you will connect the point with straight line. If you connect the point with a straight line, then you will not be able to capture the nonlinear behavior, what is happening in between the loading. So if you give a large increment of the loading, in that case, you will not be able to capture the proper nonlinear behavior. And in some cases, your deformation also will be large. Since your load increment is large, your deformation also will be large. In that case, you will not be able to get accurate data. Okay, so you should have the loading in such a way that loading is increasing smoothly, and you are able to capture the proper stress strain behavior. One more thing is there, that is your maximum loading and the minimum amount of loading. Maximum loading or minimum amount loading. So here you have to keep one thing in your mind: the loading, minimum loading should be such that your minimum loading should be such that your analysis is reaching your nonlinear zone. And loading should be such that, for example, if you know this is your stress strain pattern, okay, and you have applied the load such a way that your stress is in this zone, then whether you give the nonlinear property or not, that is not going to affect your analysis, because still you are in the linear zone due to your applied loading. Okay, so your loading should be such that it reaches to the nonlinear zone if you want to perform nonlinear analysis. Okay, so here you have to give minimum loading such that it is reaching to the nonlinear strain behavior due to your applied loading. Now this part is here for your minimum amount of load. Next is how much maximum load you can provide. Now thing is there, how much maximum load you can provide, that also depend upon your stress strain behavior. You should have some idea what is the stress strain behavior or what is the maximum deflection it can cause during the failure. So here you have to have some idea, and you have to see how much strain is occurring during the failure, and from there you can calculate what is the maximum displacement can occur. Okay, so you have to give the loading, in such a way that your analysis will go this much amount of displacement. Your analysis will go this much. Your analysis or structure will deform this much amount of displacement. If you are going for your displacement control, in that case your delta L, the displacement, you have to specify such that it is reaching to your nonlinear zone, and you are getting good result. Now thing is that if you increase very huge amount of load, in that case your analysis will take long time to perform. Some cases it may abort also. Okay, sometimes it may take large time to solve because you are giving large loading, and your analysis is trying to solve, and each time it is trying to get the result. It may take large time to give a final result. Okay, or there may be huge displacement due to your huge loading, and your analysis may abort. Okay, so this thing you have to keep in your mind while going for nonlinear analysis. Okay, in the step also you can see, you can control the increment. The step also you can control the increment. So there also you can control, but again that control, the control you are doing there, that indirectly controlling the loading, So this step you can give some time increment, you can modify something, but that will lead to your loading increment indirectly. So these are the things are there you have to keep in your mind while doing for nonlinear analysis. Now here you just see, initially I created a partition like this. I created a diagonal partition like this. Okay, so what was there? What was the problem was there? I was not able to get good condition mesh. So what I tried to did, I tried to make this part as a square. Okay, I basically surrounded the circle with a square, and then I create the partition like this, and thereafter I did the meshing. And if I did the meshing in this way, you'll observe that we are getting good condition mesh. Now once I once I go for the meshing here, I can check what are the quality of meshing is there. So you can use this verify option. So here you can use this verify options to check or verify your quality of meshing. So here you can see it is asking that your aspect ratio. So aspect ratio basically your your the ratio of the two side of your element, larger side and the smaller side. The ratio of that two side is the aspect ratio. If the aspect ratio more than 10, then you can say it's an ill condition element. Now, our poor, or you can say it is our poor element. That you can say that is our poor element. Now here, what I try to do, I'll try to highlight here. So you can see there is nothing. So you can say here also, it highlighted here. You can see it has analyzed the 10,706 element and analysis error is 0. Okay, warning also 0. So that basically indicating that we have good condition mesh and we do not have any poor meshing. Okay, so here you can do this checking. In the case of linear analysis, actually that was not creating problem, but if you are going for non-linear analysis, in that case, this will create a problem. So you should do the checking before going for your non-linear analysis. Okay, before going for your non-linear analysis. Before going for your non-linear analysis. Okay, now what we are going to do, we are going to apply the loading. So here, what happened if we apply the loading? Here you can see we have applied 100 Newton load. Okay, so 100 Newton load may not be sufficient to reach to our nonlinear zone. So what we can do, we can increase to our 1000. Okay, we'll increase the load to the 1000. And what next we are going to do? We are going to the steps, and here we'll try to change some parameter. Here this parameter we can change the minimum parameter. We can change to 1 into power minus 8. Okay, so the time increment it will take, it will be minimum will be 1 into power minus 8. Okay, and initial is one and the maximum is this one. Okay, and here it is maximum number of increment is 1000. So here basically we are changing this parameter. We'll make it okay. And next, what else we can do? We can go to the other, and here we can go for general solution and manager, and here you can click on edit, continue it. Here in the more option, here in the more options, you have some parameter that is your IA. You can do one thing, you can specify it. You just try to make it nearly 8 or 10 like that. Just click OK. Next, what you can do, you have to go for property module. Okay, here you have to go for property module. So what we have to do in the property module, you have to provide your nonlinear data here, since it is our ductile material. Okay, since it is our ductile material, what we are going to do, we are going to provide our nonlinear property. We are going to provide our nonlinear property. So here you can see we are providing your yield stress and strain data. Okay, here we are providing yield stress and yield plasticity data. One more thing here you have to keep in your mind that this plastic strain should increase monotonically, otherwise you may face some error while submitting the job. This should increase monotonically. So this is our independent variable. This variable should increase monotonically, and depending on that value, it should give your yield stress. Okay. So here you can see initially, actually, I had this type of graph. Here you can see our strain data was not increasing monotonically. So it was increasing and then it is going down. Again, it is increasing. Since it is not increasing monotonically, it was showing some error. So what you have to do, you have to delete this data. You have to delete this stress strain data, and you have to have a data like this. Okay. So I have deleted this data. Okay, and I have considered this data up to this data, and we're providing it here. Okay, so if we provide the data here, okay, as a nonlinear property, as your plastic data, yield stress versus plastic strain data, then you can submit the job, and you can get your nonlinear data. Okay, so here you have to again play with your loading and increment on the step size so that you can complete the analysis up to your desired loading, and you can check your data. Okay, so here again, this is not sufficient. Again, you have to play with your step increment in the steps, and your loading such that you can analyze, you can run the program up to your desired loading, and you can have your nonlinear data. You can have your nonlinear analysis. Okay, so this is the way you should do the nonlinear analysis for your ductile material. Next, we'll try to see how we can go for nonlinear analysis for your brittle material. Now, if you want to analyze this plate as a composite plate, and you want to analyze the failure of this plate, okay, again the failure of this plate will be brittle in nature, so you have to give the property of brittle material. Okay, so here if we consider a composite, then you have to provide your elastic parameter as well as your damage parameter. So what you have to do? You have to go to the property, and in the property there will be elastic data. In the elastic, you can choose your lamina options, or you can choose orthotropic. Okay, so this is corresponding to your linear analysis. Okay, now if you want to go for nonlinear analysis, in that case you have to. So what you have to do? You have to go to your damage for fiber reinforced composite as a Hasid damage. So you have to give the Hasid damage criteria. Here you can provide longitudinal tensile strength, longitudinal compressive strength, transverse tensile strength, transverse compressive strength, longitudinal shear strength, and transverse shear strength. So here you have to provide longitudinal tensile strength, longitudinal compressive strength, transverse tensile strength, transverse compressive strength, longitudinal shear strength, and transverse shear strength. So these are the property that you can. These are the property you can. These are the property. These are the property you have to provide. Okay, these are the property you have to provide. These are the property you have to provide, and you have to do the testing of your material so that you can find the relevant parameter. So you have to follow some standard. Okay, next you have to go to the sub options, and there you have to give some parameter for the damage evaluation and damage stabilization. That is basically corresponding to your, that you have to provide damage evaluation and damage stabilization parameter that you have to provide. Okay. Now if you go to sub options and damage evaluation, here you can see it is saying longitudinal tensile flexure energy, longitudinal compressive flexure energy. So here energy, so you can give some value. Whatever you do, you have to do 4 testing. One is longitudinal tensile, longitudinal compression, and you have transverse tensile and transverse compressive. So here you have to do 4 testing, and you have to obtain your stress strain data. You have to obtain your stress strain data, and you have to find the curve under it. You have to find the curve under it. So once you save the data, either you find the area using your mathematical tool, or you can save the stress strain data as a JPG file, and you can use some MATLAB toolbox to get the area under the curve. Okay, so this is the way you can find. Next, we have damage stabilization parameter. The damage stabilization parameter, you have to give some here 1001, 1001, like it 1001. The brittle material, what you have to do, you have to first provide the elastic parameter. So these are the elastic parameter. Okay, and then you have to provide same data corresponding to your Hasin damage criteria, corresponding to your Hasin damage criteria. And as per your Hasin damage criteria, you will provide longitudinal tensile strength, longitudinal compressive strength, transverse shear strength, okay, and longitudinal shear strength, longitudinal shear strength, okay. So now if you have a bidirectional composite, okay, in that case, your longitudinal shear is longitudinal compressive strength. In that case, your first four data will be 473, 473. If you have a bidirectional composite where you have the same E1 and E2, okay, in that case, your this parameter will be first four parameter will be 473, 473, okay, and your last two parameter will be 85, okay. So this is the way you have to provide your property, okay, in your Hasin damage criteria. And again, at the end, you have to provide your damage evaluation parameter. So damage evaluation parameter that you have to provide, which is coming the area. You have to find the area under the curve, and you have to provide that value. And in the damage stabilization parameter, you have to provide some parameter. This is the way you have to model your composite material. One more thing you have to keep in your mind, along with that material property, you should have a proper meshing, you should have a loading, and you should have a increment. In the statement, you have to, so along with your material property, there should be proper meshing. You should have a loading so that it is reaching to your nonlinear data analysis. It is reaching to your nonlinear analysis. Step increment, you also can control the step size. Okay, these are the things you have to do. One more thing you can do here, if you observe that you are not able to solve it, then you can go to solution manager. So here in the solution manager, you can control some parameter, that IA parameter, you can make it to 8, 10 like that. Okay, and you have to see again, you have to do some trial, get your solution. Okay, to get your solution. So these are the things are there you have to keep in your mind while doing the nonlinear analysis. Okay, so again, it is very tedious job. You have to do many iterations, you have to do many trials so that you can get your desired result. So I hope you get some idea. Thank you. In some cases, so here what we are doing, we are applying the load in one direction and other degree of freedom are free. Okay, so in many cases, if you are doing some nonlinear analysis, okay, in some cases you may get some warning or error. So what you can do, you can fix other degree freedom. Okay, you can fix other degree freedom, only you can make it, only you can free that x direction, okay, or loading direction. So you accept your loading direction, you can constrain the other degree freedom so that you can avoid some error which is causing due to that free node or free degree freedom here. Okay, due to some free degree freedom here. Okay, so these are the things this thing also you can